Okay, guys, you see now we have a new chapter. This is about additive manufacturing. AM stands for additive manufacturing and CNC process planning. CNC means computer numerical control, and we will always referring to CNC machining, but I keep the title short, so I didn't write machining here. But once we refer to CNC, as you know, in the industry, they are mostly referring to CNC machining. So what about the differences between these two methods, the two manufacturing approaches? And the first one, additive manufacturing, as the name implies, we are adding the materials on top of each other so that the part will be fabricated. But in the CNC type of other type of manufacturing systems, subtractive type of manufacturing systems, we start with a block of material and then remove material with the help of special tools and try to manufacture various parts. Yes. Obviously, the first one is additive, the second one is subtractive. And we also have computer numerical control in additive manufacturing, but this is taken as granted. We don't even talk about it. Obviously, additive manufacturing systems are all computer numerical controlled. And another differences in the additive manufacturing, we have support structures while reviewing some methods. I will briefly discuss them since you cannot add material in air. If the material is in air, then you need to have some extra support structure underneath so that you will keep that deposited material in position. And this is done with the help of support structure, but obviously in the CNC machining side, we don't have such cases since we start with a block of material. And in additive manufacturing system, we mostly have 3-axis systems. These days, there are also 5-axis approaches, robotic approaches, but the conventional additive manufacturing machineries are all 3-axis. And on the computer numerical control side, we have 3 to 5-axis CNC machineries. And in this chapter, we'll be talking about process planning and path planning of these approaches. Let's start with the additive manufacturing. And we have many methods, but we are not going to cover all of them in this chapter, since this is a kind of a review of additive manufacturing systems. But the first part might be quite useful since your 4th project is about, some part of your 4th project is about a path planning of physical position modeling or physical fabrication systems. And this was a bonus part, if you remember. So you may do it if you would like to, but it's not a must. You may simply skip it if you don't want to spend time on the generation of paths for physical fabrication. Then we will briefly go through selective laser sintering, SLA and DLP, and lastly, we will briefly talk about sheet lamination systems, and they are all additive manufacturing methods. Let's start from the first one, fused filament fabrication. And by the way, this is a trademark of a company, FDM, fused position modeling, but we prefer to use fused filament fabrication, and this is the name given by the International Standard Organization, so that's why we prefer this one. But they are all the same approach, referring to the same approach. Oops. Here we have a video. I think, as far as I remember, this should be embedded, but let me check it. No, this is not embedded, so I will copy this one and then share the screen with you and have a look at this.
Introducing.
Okay, now I will share it with you. Yes.
The Ultimaker S5.
This is one of the pro-consumer type of 3D printers, desktop 3D printers, and it's using fused filament fabrication methods.
Most reliable, versatile, and easy-to-use desktop 3D printer. Engineered for printing prototypes, manufacturing aids, and end-use parts, let's see what makes it the complete, user-friendly 3D printing solution. The Ultimaker S5 features the largest build volume yet in an Ultimaker 3D printer, so you can print bigger models or put more parts on the build plate for maximum efficiency. To ensure repeatable, high-quality prints in an efficient workflow, the Ultimaker S5 is built around seamless integration of hardware, software, and materials configuration. Ultimaker Cura software optimizes your settings for larger prints.
So this is a kind of software they are using for printing. They start with the STL format of the design, and then here in this CAM software, complete manufacturing software, they actually take slices of this part, and then generate the paths for the deposition of material.
Optimizes your settings for larger prints.
And obviously they have many settings: slicing thickness, nozzle diameter, the color of material, the melting temperature of the material, the speed of the nozzle. There are many parameters, and obviously they have default parameters. If you don't want to deal with the parameters, you can continue with the default ones.
While Wi-Fi and Ethernet network capabilities mean you can print from your desk. With Cura Connect on your desktop or via the app, you can monitor prints and manage your 3D printers. Touchscreen navigation on the printer makes setup and maintenance fast and simple. In addition to the glass build plate, the Ultimaker S5 also features an anodized aluminum build plate, which is designed to make printing with engineering materials easier, while also giving a more consistent surface finish to the bottom of your part. With 2 build plates, you can choose the one that fits the material. Before your print starts, the active detailed bed leveling system corrects any offset on the build plate surface.
So this is the first actually level which your product is to be printed, and its level is highly important. It should be perfectly leveled, otherwise you'll have problems during your print, and that's why this machine is going to level it by using some capacitive type of sensors in its head. And another important issue with the table is that once you start printing, your part should actually properly stick to the plate. If it doesn't stick well, then again, in the upcoming slices, layers, you'll have problems.
A sensor scans the plate at multiple points, and the build plate height is adjusted to compensate and give a perfect first layer every time. Closing the doors of the Ultimaker S5 gives you better control of the temperature and airflow.
Another important issue is the temperature, since you will see in a moment that the material is actually fed into this nozzle, and at the tip of the nozzle, the material is quite melted and it's deposited on the table. Another thing, if you have some special materials, engineered materials, then you need to also control the temperature of the environment. If you have temperature fluctuations around, then the quality of your print will be problematic.
This, in combination with using the right build plate and active bed leveling, ensures good adhesion and reliable 3D printing. Ultimaker's dual extrusion technology gives unparalleled reliability. Printing with 2 materials, you can produce technical parts with cavities and overhangs supported by specialized support materials. Realize your most complex designs in PLA, nylon, or CPE combined with PVA support material that dissolves away in water, enabling complete dimensional.
So these are the type of nozzles. The materials are extruded into this opening, and then they are heated at this tip and extruded through this nozzle. And you see they have different nozzles for different materials. For instance, this BB 0.4 is used for water-soluble materials, and these are especially preferred for support structures. Once you have water-soluble support structure, then after the print is over, you can put your part inside a water box and remove the support structure without giving extra effort.
Freedom in design. And when you need to adjust your printer setup for a different material or nozzle size, material matching print cores and NFC-enabled filament spools ensure quick changes and high uptime. The Ultimaker S5 is a flexible platform for creative designers and engineers. Depending on what properties your prints need, you can choose from a wide range of optimized Ultimaker materials or other filaments thanks to S5's open filament system. Whichever material you select, the intuitive touchscreen interface guides you through the printer setup for easy, first-time right configuration.
So you see how they are printing. This is a single slice, the first slice, and it's highly important since it should stick to the table properly.
The Ultimaker S5 comes with Tough PLA, a technical material with toughness similar to ABS, but
so they have various materials. You don't need to use a single material. They have PLA, PVA, ABS. There are many thermoplastic materials. Some has high toughness values, some has high elastic values. Depending on your application, you can find the proper material and
simplicity of PLA. Ideal for rapid prototyping with large prints. Tough PLA is compatible with Ultimaker support materials, including PVA. For the perfect printing results, use our material range with pre-configured profiles in Ultimaker Cura software, which have been extensively tested and optimized by our engineers. Sensors monitor your filament flow during printing. If the material runs out, the printer pauses and notifies you to load new filament before resuming. With the Ultimaker S5, you choose a future-ready 3D printing solution that will grow even richer in functionality and possibilities over time. Regular firmware updates add new and optimized features alongside improvements to Ultimaker Cura and Cura Connect software. The Ultimaker S5 feeder is designed to print with advanced technical plastics such as composite materials. Over time, more materials and print cores become available, opening up even more possibilities and applications. The Ultimaker S5 is the powerful, reliable, and versatile 3D printer that delivers industrial-class results. With Ultimaker's complete integrated solution, professional 3D printing is made even more accessible.
Okay, now let's go back to the slides and you'll have more insights into the freeze filament fabrication methods. Do you have questions, guys, about this video? Maybe basics of freeze filament fabrication? Okay, let's continue with some other features of freeze filament fabrication. So this is summarizing the main steps in freeze filament fabrication. You start with the CAD model, might be any CAD model, any CAD software may be used, and then you convert your CAD model into an STL model. If you remember, this is a mesh file format. We have triangles inside, and then you import this STL model into the CAM software. So this is done on the CAM software. We try to find the best orientation for printing since we may need to use support structures. These are the red ones are the support structures. Depending on the orientation, you may need to have more support structure or less, even sometimes in a specific orientation. You may even not need any support structure. So the orientation is highly important. And after you've determined the orientation, the best orientation, you can generate the support structures if required and do the slicing. And in slicing, as you have done in the third mini project and you are doing in the fourth, we are taking the slices at various Z heights, and the thickness of each slice is equal, they are constant. And then another thing CAM software is doing is that it generates these infill patterns. You see we have complete the field interior. This is a kind of a zigzag pattern. And then after you have the paths generated, you kind of generate later a job file. And most of these desktop printers are using G-code files. And after you have the G-code file, then you can transfer this G-code file to your printer. over Wi-Fi, over Ethernet, or USB, and then start the manufacturing process on your printer. If you look at the slice here, we have some shells. These shells are again related to your mini project. Let me draw this. Assume that is the outer boundary, and then we have a shell here. And we prefer to have at least 2 shells so that the part will have some amount of strength. You may increase it, but 2 or 3 is quite fine. And then depending on the settings, for instance, probably this infill percentage is 100%. But if you want to have less material inside, then you may have such a sparse infill. Probably this might be 30% or less. And you consider that the width of these actually beads depend on the nozzle diameter. And in most of the twist welding fabrication systems, the nozzle diameter is usually 0.4 millimeters. And that might be variable in your project. So one can simply update this nozzle diameter. So each line, you can assume that has a thickness of 0.4. And after these paths are generated and transferred to the machine, then your printer will start extruding material once the nozzle is heated enough. And once a layer is fabricated, your table will go down a little bit for the next layer, and then it will start depositing the material for the next layer. And these will be repeated for a number of layers, and you will have your part fabricated. Any questions, guys, about these fundamentals? Some of you are already familiar with these, and for the rest, it might be quite new. Please make sure that you understand these fundamentals.